Hello, Rose Dawson. A similar suggestion was made a few years later by the French scientist, the Marquis de Laplace. You know Laplace, right? Apparently independently of Mitchell. Interestingly enough, Laplace included it in only the first and second editions of his book, The System of the World, and left it out of later editions. Perhaps he decided that it was a crazy idea. Also, the particle theory of light went out of favor during the 19th century. It seemed that everything could be explained by the wave theory. So, right, there was a lot of development in electromagnetism, which is the wave theory of light, with all those people, Faraday, Maxwell. They contributed immensely to, of course, the electromagnetic theory. And in that theory, the speed of light was a constant, and it just kind of falls out as a constant of nature. The speed of light in vacuum, that is. And so all this like wave theory of light really kind of took over. So in the 19th century, which would be the 1800s, light was basically more a wave than anything else, whereas really in the 20th century, it started to have a particle nature in our understanding, like, you know, photoelectric effect. The old quantum mechanics was really literally Einstein and others contributing to the particle nature of light, along with the wave nature of light. Chat is slow again. We need some action. Go ahead, guys. I'm loving it. Bring out the chickpeas. That's true. I might actually make chickpeas in a little bit, but let's do a little bit more reading and studying first. Thank you so much. Thank you so much for being here. If you want the chat to be more active, you should share the live with every relative and friend and coworker. Harper! We need singing and shit. Hi, Harper. Hello. So let's keep going for a little bit, and then we will have singing and chickpeas. Okay. Give me a moment. Also, the particle theory of light went out of favor during the 19th century. It seemed that everything could be explained by the wave theory, and according to the wave theory, it was not clear that light would be affected by gravity at all. Yes! In fact, it is not really consistent to treat light like cannonballs in Newton's theory of gravity, because the speed of light is fixed. A cannonball fired upward from the Earth will be slowed down by gravity and will eventually stop and fall back. A photon, however, must continue upward at a constant speed. How then can Newtonian gravity affect light? That's a very good question. Does it affect light? Does anything happen with light in Newtonian gravity? Thank you. A consistent theory of how gravity affects light did not come along until Einstein proposed general relativity in 1915. So this updated theory of gravitation was very much needed in order to understand the effect of gravity on light, because as far as Newtonian mechanics goes, I mean, you can't really affect light. Light has a constant speed. The speed of light in vacuum is a constant of nature. So it will always travel at that speed in vacuum. And so as far as Newtonian mechanics goes, things with mass accelerate under gravitation, etc., etc. So the picture of how light is affected by gravitation is really not, doesn't really come together until Einstein worked on his general theory of relativity. Even the special theory of relativity was not really enough, because it is something that holds true for inertial frames of reference when things are moving at a constant speed, in other words. So if you're under some kind of acceleration, then it doesn't really hold true anymore. And he knew that he would have to work on a more general theory of relativity in order to explain more general things.